I'm Dr. Bob Hogg, and in this video we're going to be having a look at effect sizes. Now this is quite important because it's a key aspect of classical type statistics, but also because we're looking at JASP, we're also looking at Bayesian statistics, and it is in fact the effect size that is being measured in terms of the Bayesian analysis. So let's have a quick look at what effect size is and what are the limitations of the p-value, for instance, when we look at classical statistics, which is why normally academic journals require both p-values and effect sizes to be included in any analysis. And we'll also have a look at some key effect sizes, and this is not an exhaustive list but just gives you some an indication of some of the effect sizes that you might see in the literature and indeed inside of JASP. So if we have a look at what's in this particular presentation, we'll have a quick look at why we have to use effect sizes, or why we should use effect sizes, how this has been introduced in the last few years due to the limitations of the statistical significance or p-value, and then we'll have a brief look at one of the effect sizes, and you can see there's many in this list, again not exhaustive, but to see what the effect of effect sizes is as opposed to p-values as we increase the sample size. So effect size is an actual way of measuring how big the difference is or relationship between two quantities in a study. It is actually a measure of the effect that we're looking for in our scientific experiment. And if you look back on the video on Bayesian analysis, you'll see that this is exactly what Bayesian analysis does. It looked at this effect directly and continuously updates its information as you add more and more data. So again, if we look at the concept of looking at two groups, the effect size tells you what the difference is, as well as telling you if there is a difference. The p-value simply tells you whether or not there's a statistical difference. Now this can be very important in real life studies because it tells you whether or not something works better or some effect is more noticeable or is more useful. In other words, it has real world importance in terms of a measurement of a real effect. So there are some limitations in the concept of statistical significance, and again, if you go back to the video on statistical significance and p-values, you'll see that in effect the p-value just tells you whether or not the effect that you're observing is a real effect, or could it just be due to sampling error or random chance. So effectively it is based around about the standard, based on the standard error of the mean generally, if we're looking at, for instance, the difference in the mean between two groups. And because effectively this standard error is a mathematical formula dependent on the number of samples, then it is very dependent on sample size. As such, if you have very large studies, quite often you get a significant result simply due to the sample size, and that's what we'll be having a look at in the experiment, which we'll be doing shortly. So again, one of the other main reasons why this has been included or is a requirement now for different types of studies, if they're to be published, is that it can also be somewhat misleading if, for instance, the study design is flawed, or for instance if somebody is doing what we call p-hacking, which means they've got a very large sample in a very detailed study and they've essentially just looked around looking for significant values. What you should do in practice is actually state what you're looking for at the start of the study, and then actually go and seeing if you can set up a hypothesis and then prove or disprove that hypothesis. So they are the limitations. So let's do a little experiment, or let's have a look at one particular effect size. And the one we're going to look at is probably the most common one, which is Cohen's d, but other common ones include things like Pearson's R, for instance, the R squared value, odds ratio, and logistic regression, for instance, eta and partial eta squared, for example, and many others. Some of the ones down in this list you might not be too familiar with, and there are others besides. Again, there are others actually included within JASP, and you may want to sort of explore them in some detail. So if we have a look at this Cohen's d, which we're going to be looking at, it is usually used in the measure of the differences between two means in standard deviation units, and as such we're going to essentially look at a simple t-test, and we're going to look even simpler. In actual fact, we're going to look at a one samples t-test and see how Cohen's d, standard error, and the p-value changes with sample size. The other thing you should be aware is you do need to do a lot of work before your study in terms of effect sizes to have a look at how they're interpreted. The actual values associated with what might be regarded as a large or a small or a medium effect can vary fairly substantially, and so you should look at that in some detail, find out whether or not these values are bounded. For instance, a correlation coefficient is between -1 and +1, or whether or not they can go outside certain bounded areas. So again, a lot of work needs to be done when you're doing anything of this nature. So let's now have a look at an actual example in JASP, and to do this, what I've done is I've basically generated a data set, and this is based on a little bit of research where I've done to find out what the mean height of UK males is and what that standard deviation is approximately, and this comes out to be 176 centimeters with a standard deviation of about 8 centimeters. And what I've actually done is generated a whole list of these values which are randomly distributed, and in fact I've done 10,000 of them, so I can sort of choose how many to use in my particular experiment. You might be interested how I generated this data, because that was done by JASP, and if you notice here, I've loaded in from the modules menu the distributions option, and if you look in this distributions option, you can see that just about every distribution you could possibly imagine, both discrete and continuous, are included here. And what I've done is I've looked in the normal distribution, which is probably the one you're most familiar with, and within that normal distribution you can specify, for example, a mean and a standard deviation or variance, and then actually display this, or more importantly, you can actually generate and display the data. So what I've actually done is I've set up the mean of 176 and the variance of 8, and I've generated that data and in fact used 10,000 samples, or generated 10,000 samples by just clicking on the draw samples button. So this is quite a useful way of generating test data for any of your particular studies. So what I've actually done here is the male height at 176,8, which shows the mean and the variance. And what I've also done is, just to show you as the second part of the experiment, that it's not just the order of that the data is being generated. I then randomize that order and then set up two ID variables, one of which is based on this order and one of which is based on the original order, just to start to filter that data to use different sample sizes. So, as I said previously, what we're going to be looking at is a t-test, and in particular we're looking at a one samples t-test, because that is probably the simplest t-test that there is and should be the easiest one to essentially look at the results and work out what's actually going on. But I'll get to that shortly. If I go back and edit the data, the other thing I'm going to do is to actually filter the data to use different sample sizes. And to do this, I'm just going to click on the filter button. Again, there's a video which shows you how to do this. And based on that, I'll just sample on this first order data set, which is ID2. I'll bring ID2 into here, and I'll just look at the first 10 data samples by looking at the values that are less than 11, and then what I can do is apply this pass-through filter, and what you should be able to see if I just scroll this up slightly is that it has indeed selected the first 10 samples, and I'm going to change this as we go through. So if I go back to the analysis, what I'm then going to do is to set this up to look at my height variable, and I'm going to look at the Z test, which is essentially the normal test. So again, it's as close to what you would think is the data that I've generated. I'm also going to look at the difference, or look at a very small difference. In fact, I'm going to look at 177, and I'm going to sort of match up that standard deviation. For instance, I'll make it 8 there, and I'm going to look at the location estimate, effect size, and descriptives for that data. So what you can see here is, especially if I look at a rain cloud plot, which will probably be the easiest one to visualize, you can see I've got 10 data points here, I've got the bar plot, and I've got the distribution of those data points, and here is my fixed value, which you get within a single samples t-test. Now, what you can see here is a number of various values. You can see that the mean difference is 1.199. The mean of the actual sample is 175.8, and that's being compared to this 177. We have 10 data points, we have a standard deviation, and we have a standard error. Now again, what we're going to see is, because the standard error is based on the standard deviation and the sample size, is that value will drop as we increase the sample size. The other thing we need to have a look at is the effect size, which is the Cohen's d value. So again, as these various parameters change, the standard error for instance, and associated with that the p-value, and we should also compare that to how Cohen's d changes as we change the sample size. As you can see at the moment, we have a non-significant p-value of 0.636, and so there isn't a difference between this fixed value and the average height for our sort of male population, which is 176. So let's now go and change some values and see what actually happens to these figures. So if we go back into edit data, we can sort of increase the amount of data by just changing this, for example, to 21. We'll apply the filter again and go back to the analysis. And you can see Cohen's d has changed ever so slightly. The p-value has dropped quite a lot because the standard error has dropped quite a lot as well, because obviously we've gone up to 20 samples. Obviously the calculated mean has changed as well. So let's keep on doing this. Let's move it up to 50. Again, we'll reapply the filter, go back to the analysis, and just takes a second to put the data back in. And again, you can see Cohen's d is still hovering around about this 0.15. Notice now the p-value has dropped even further, and that's sort of reflected obviously in the z value, which is where the p-value has been calculated from, and the standard error is also dropping. So again, we can go back, edit the data yet again. We'll go up to 80 values, apply the filter, go back to the analysis, and again this Cohen's d is still hanging around that 0.15, but notice how the p-values yet again dropped because of the standard error dropping. Let's go to 100 samples now. And you can see Cohen's d value has changed very slightly, but it's still around about this 0.1 to 0.2. But now notice how the p-value is almost statistically significant. It's just above that 0.05 level because the standard error is still dropping. So that's at 100, and so you can imagine if we go to something like 1000 samples, back to the analysis, then you notice again Cohen's d is still around about that 0.1 to 0.2, so the effect has not changed, but the p-value is now highly statistically significant. So again, this is one of the problems with p-values as the sample size goes up. So in this particular case, the z-score or the t-score will go up, and this will become statistically significant because the standard error is dropping to quite a low level. So finally, we can put this up to the full sample size. See what we get. And again, you can see the Cohen's d is about 0.12 again. The z value is -12, so huge. So the p-value is going to be absolutely minute, and the standard error, not surprisingly, is very, very small. So what this experiment is actually showing is that as we increase the sample size, such as going from a small sample of 10 up through 20, 50, 80, 100, to 1,000 to 10,000, so the p-value tends to become very, very small, and so you get a significant result, even though the effect, which is measured in terms of the Cohen's d, which albeit is a small effect, has not really changed that much. And so that is one of the problems with p-values, which is why you should always use the effect size as well as the p-value in these particular cases. So what I can do, just to make sure that you don't think it's this particular order that's making the difference, I can actually change this to the first ID number, and again that is just going to select values randomly from the list instead of sequentially down this list. And so I can do the same sort of thing. So start off with the 10 values, look at the analysis, and we should get something very similar. Again, the Cohen's d is very similar here. The p-value has changed to a certain extent because of the new data that's come in, but it is still non-significant. We can go and stick in much larger values very quickly on this new data set. We'll go up to that 100 value, see where we are. P-value hasn't become significant yet because of the different data. The Cohen's d value is again sort of hovering around this area. Again, go to 1000 samples. As I said, with the different sample set you will get different values, but notice now the p-value has become highly significant. Cohen's d has not changed particularly much here, and so we're seeing the same sort of pattern as we saw in the other data set. So the order of the data really doesn't make much difference in this particular case. So the important thing to bring out of that experiment is that you should be very, very careful to include both p-values and effect sizes in terms of your analyses. And again, just to finish off, we can also put into this particular example, or this particular experiment, a Bayesian t-test, again where we can do the same sort of thing, and we can look at a particular test value, and again there are no particular differences that we need to look at, but we'll look at 177. We can look at the prior and the posterior, and we can have a look at the sequential analysis. And what you'll find is that as you get a bigger and bigger sample, this distribution, or this posterior distribution, which is the posterior distribution of the effect size, delta, here, will get narrower and narrower. And you can see here, as we looked at in another video, is as we get more and more data, the effect does start to increase and becomes more prominent, and there is more evidence for the hypothesis H1, which means there is a difference, or a difference is being observed. So that's that particular experiment. Hope you've found this useful, and what I would recommend is that you look at a lot more data on different types of effect sizes and do some experiments yourself within JASP.